Have you ever stopped to think about the hidden language of the universe? I mean, it's all around us, right? It's in the electrical signals firing in our brains, it's in the chaotic rhythm of the stock market, even in the slow, deep patterns of our climate. For 100 years, we've been trying to decode this language, but the signals are just, well, they're a mess. They're too complex. But what if we finally found a way to translate it? A universal key? That's what we're digging into today. See, the core problem has always been that a single signal is never really just one thing. Imagine you're listening to a full orchestra. You've got the slow, deep rumble of the cellos. You've got the main melody from the violins. And then you have the fast, high-pitched notes of the piccolo, all playing at the exact same time. Real-world signals are exactly like that. A jumble of slow waves and fast spikes. And trying to pull them apart to hear each instrument clearly has been almost impossible. And for the longest time, our tools just weren't up to the task. Things like Fourier transforms or wavelets, they were amazing for their time, but they have a massive flaw. They either have to assume that a signal is perfectly stable and never changes, which, let's be honest, it never is, or they need a human expert to sit there and manually tweak and fine-tune them for every single new problem. It's just slow, it's inefficient, and it really struggles to capture the dynamic messiness of the real world. So that's the big challenge, right? How in the world do you build a single tool that can listen to that entire orchestra at once and then automatically separate the cellos from the violins from the piccolos for any piece of music without a conductor telling it what to listen for? Well, the breakthrough comes from a really simple but pretty profound shift in how we look at the problem. Instead of trying to analyze that one messy, tangled-up signal, what if we could teach an AI to see it as a stack of different layers, with each layer moving at its own distinct speed? And this slide. This is a fantastic way to think about it. Look at the leopard. The low-frequency part of the signal is like the forest. It's the big picture, the overall pose of the animal. The mid-frequency is the trees, the main shape, the body parts. And the high frequency is the leaves, all the fine details, the textures, the individual spots on its fur. Turns out, basically every signal in nature has this kind of hidden structure. And that brings us to the star of the show, the Universal Signal Decomposition Framework, or USDF for short. It's an AI that has absolutely mastered this forest, trees, and leaves analysis. It's a single, powerful model that can take any signal you throw at it, brainwaves, stock prices, you name it, and automatically learn the best way to break it down into these meaningful layers. But here's where it gets really clever. The genius of USDF isn't just that it can split a signal into 3 parts. The real magic is in how it treats each of those parts. It understands that the rules that apply to the forest are totally different from the rules that apply to the leaves. So how does it actually work? Well, at its core, it uses a type of AI called a variational autoencoder, or VAE. The easiest way to think about a VAE is like a brilliant archivist. First, an encoder reads a whole book and writes a super compressed summary. That's called the latent code. Then a decoder takes just that summary and tries to perfectly reconstruct the original book. What USDF does is it supercharges this process. It creates 3 of these summaries at the same time, one for the low-frequency forest, one for the mid-frequency trees, and one for the high-frequency leaves. Okay, and this slide right here, this is the big aha moment. On the left, you see an image. For an image, the big picture, low-frequency structure is pretty predictable, right? So the model compresses it heavily. But now, look at the right. That's a brain signal. For a brain, those slow, low-frequency waves are not background noise. That's your cognitive state. It's the most important part of the signal. So USDF does the exact opposite. It applies very gentle constraints, preserving that vital information with incredible care, while it aggressively compresses the noisy high-frequency chatter. It's the same framework, but it's smart enough to apply different rules to different signals. So here's the key takeaway. You wouldn't pack a suitcase the same way for a weekend trip to the beach as you would for a month-long expedition to the Arctic. USDF is like an expert packer. It knows what's important for each trip. For images, it tightly packs the predictable background. For brainwaves, it gently handles the crucial cognitive state while squishing down the noisy static. This whole idea is called differentiated regularization, and it is the absolute secret sauce. And does this smart design actually pay off? Oh yeah, the results are pretty stunning. USSDF can reconstruct a signal with 93% accuracy, which is a 33% improvement over standard models. And it does it all with a blistering fast latency of just over 7 milliseconds. So it's not just more flexible, it's more accurate and way more efficient. Okay, so we've got this really elegant theory, but this is where we go from theory to something that sounds like it's straight out of science fiction. a security system that you unlock, literally, with a thought. Say hello to Project Encephalon. It's a neurobiometric system built entirely on USDF. Forget passwords or fingerprints. With this, you have a pass thought. It's a unique combination of mental images that only you can create. Something like imagining the smell of fresh coffee, seeing the color blue, and hearing the sound of ocean waves, all at the same time for just a few seconds. And how well does it work? Just look at these numbers. They are absolutely wild. Project Encephalon has a 99.7% true acceptance rate, but what's even crazier is the false acceptance rate, 0.01%. That means it would let the wrong person in only one time in 10,000 tries. And it makes that decision in 7.2 milliseconds. That's hundreds of times faster than any other brain-based system out there. But here's the kicker. Here's why it's truly unbreakable. It has 3 security features built right in. First, liveness detection checks for specific brain waves that only a living brain produces. Second, duress detection can actually sense if you're being forced to unlock it by analyzing stress patterns. It'll open the lock, but silently send an alert. And finally, it can tell if an AI is trying to fake your brain signal. This isn't just a gimmick. This is the kind of ultimate security key you need for something like controlling an artificial general intelligence. Now, as mind-blowing as Project Encephalon is, it's really just one application. The true power here is that USDF is a universal tool. It's like a Rosetta Stone for decoding complex signals, no matter where they come from. And that's the beautiful part. This one single framework that can read your thoughts can just be pointed at a totally different problem. For financial data, that low-frequency band becomes long-term market trends. For climate data, it's seasonal cycles. It automatically figures out what the forest, trees, and leaves are for any signal you give. And the results in these other areas are just incredible. In healthcare, it can give a 28-minute warning before an epileptic seizure happens, giving someone time to get to safety. In finance, it spotted a major market correction 19 days before it hit. It can predict El Niño 6 months out with high accuracy, give almost 4 days of warning before a critical piece of factory equipment fails. It can even be used to spot financial corruption. It's just staggering. So what does this all add up to? Well, it's more than just an improvement. It's a fundamental shift in how we do things. We're basically seeing the end of an entire era of signal processing, an era that was all about manual, handcrafted work. You know, the old way meant a brilliant expert had to sit down and design a brand new tool from scratch for every single new problem. It was slow, it was expensive. The new way is to build one universal, incredibly powerful framework that learns the best solution all on its own, just by looking at the data. The deep learning revolution that changed things like computer vision, well, it's finally here for signal processing. And look, the numbers don't lie. It's not just more flexible, it's just flat out better. This table compares its error rate, where lower is better, against all the classic methods. USDF has the lowest error by a significant margin, making it the most accurate, all while staying incredibly fast and efficient. So, at the end of the day, it all comes back to this one beautiful, unifying idea. The signals that make up our universe, they are naturally multi-scale. There are always big things happening slowly and small things happening quickly. By building that fundamental truth directly into the architecture of our AI, we get models that aren't just more powerful, but they're also easier to understand and more reliable. This is so much more than just another analysis tool. It's a completely new lens for looking at the world. It gives us the power to break down any signal, from the symphonies of the cosmos to the quiet whispers of our own biology. And that leaves us with a really profound question. Now that we finally have this universal translator, what complex system are we going to choose to understand next?